Hello, everyone. I hope you are doing well. Today, we will discuss the third model for classification, which is the Gaussian Naive-Bayes models. If you remember, we discussed the K, uh, KNN, K nearest neighbors, and the logistic regression models. And this is the third model that we are going to discuss today, and mainly is based on the Bayes rule, and which is one of the famous, well-known probability rules that most likely you learned it from the stat course. So I'm going to review the Bayes rule, but before explaining the Bayes rule, I'm going to start with the law of total probability of the rule of elimination, which is a simple rule. And this is the formula and the theorem for the law of total probability. So I'm going to explain it using a Venn diagram. Assume that your space is partitioned to three different subspaces. Let's call them B1, B2, and B3. So as you can see, these subspaces are mutually exclusive. That means there is no overlap between these subspaces. Another thing is none of them are empty, and the union of all these three subspaces gives you the total subspace that we are talking about. So a collection of subspaces that have these three properties is called a partition. So the intersection between any two subspace, I and J, is empty. For any J, the subspace cannot be empty. The subspace by itself is not empty set. And finally, the union of all of the subspaces, let's say Bi, union of all of them gives you the whole space of the probability that we are interested in. So assume that I'm going to compute the probability of an event like A. And as you can see, the event A, part of it is happened in subspace B1. Part of it is in subspace B2. And part of it is in subspace B3. So the probability of A depends on the probability of the subspace and the portion that happened in that subspace. So very simple. So the best way to write it down, this probability, is using a technique that is called the a tree diagram. So in a tree diagram, first of all, you have branches based on the main subspaces. So for example, here we have three main branches, P1, P2, P of B1, P of B2, and P of B3, because we have three subspaces. And for each branch, you have to compute the conditional probability of A given that branch. For example, P of A given B1, P of A given B2, P of A given Bn, if we have n subspaces. Then you multiply the probability of that subspace to the conditional probability, and then you sum them up. So the total probability, because of that, is called the total probability. That the total probability of A equals to the probability of the A given that subspace times the probability of that subspace. This is called the law of total probability. So let's see how can we compute the total probability of an event when we have a partition of the sample space. So in this example, let me clean up my drawings first. As you can see, in this scenario, there are three rental cars companies. So three rental cars. So we have three agencies. Let's call them agency one. So I'm going to use A1. So P of A1 is 60%. So the number of cars that rented from the agency one is 60%. So P of A1 is 60%, 0.6. That's branch one. In branch P of A2, the probability is equals to 30%, which is 0.3. And for branch 3, P of A3 equals to 10%, which is the last agency in this scenario, so which is 0.1. So what we want to do is, we know that the 9% of the cars from agency 1 need an oil change. Okay, the main thing is oil changing. So for the first branch, we know that the P of A1, given that we know that we need the oil changing, is equals to 9%, 0.09. And for the second one, P of A2, the probability that we know that in A2 we need the oil change is 20%, which is 0.2. And for the third one, P of A3, given O, equals to 0.06, which is 6%. So assume that we have ordered a car, a rental car, and they deliver the car. What's the probability that this car need an oil change? Yeah, that's the things that we are interested in. So P of oil change. P of O equals to what? So as we discussed, the total probability is the multiplication of probability of each subspace times the conditional probability, And then we sum up all of them. So 0.6 times 0.09 plus 0.3 times 0.2 plus 0.1 times 0.06. So you can use a calculus to see what's the probability of a delivered car that needs an oil change. Okay, so now that we know the law of total probability, I can explain the Bayes rule. And I'm gonna clear the drawings and move on to the next page, which explains the Bayes rule. So in the Bayes rule, instead of computing the total probability for any event like A, we interested in to what's the probability that this event A that we interested in is in the sample space S belongs to one of those subclasses. So I'm interested in, for example, in the oil change scenario, I'm interested that, okay, let's assume that the car needs an oil change. Yeah. So what's the probability that this car that is delivered belongs to agency 1 or belongs to agency 2 or belongs to agency 3? Yeah, one of these probabilities. We do the reverse probability. We are interested in the not in the event. We're interested in the subclass. What's the probability that this event happened in that subclass? So you see that here helps us to use this Bayes rule for classification. Yeah, we are not interested in that event. We are interested in the classes. Yeah, so the classes that has the highest probability, most likely the sample belongs to that class. So we use this rule to do the classification. You see that, how it connects to the classification problem. So let's solve a problem. For example, we have a rental car that needs an oil change. So we want to see what's the probability that this car coming from the rental agency number 2. Yeah. So P of agency 2, based on the fact that we know that needs the oil change. Yeah. We want to compute this probability. So, and that's simple. You remember that we computed the probability of oil change in the previous slides. That was the total probability. This one was the total probability. So the denominator is the total probability, and the numerator is just for the second branch. Yeah, so I'm just interested in the second branch. So in the second branch, if you remember, I believe 30% of the cars coming from the second agency, which is P of A2, times how many of them needed needed oil change? I believe 20%, which is times 2.02. So the numerator is just the multiplication of the probability of the given subspace times the conditional probability divided by the total probability. That's the Bayes rule, which is the building block of the Bayes classifiers. So I'm gonna clean this page and move on to the next page and explain how a naive Bayes model works. Yeah. So we can explain the naive Bayes models, uh, which is a Bayesian classifier technically, um, using some graphical models like the one that you see at the bottom, right bottom of this page. Yeah, bottom right of this page. So we have a single cause. For example, uh, uh, in the penguins example from the Zai books, or the seeds, wheat seeds that we discussed in the class. So we have um, seeds, three type of seeds, yeah, uh, comma, rosa, and Canadian. These are three type of wheat seeds. So that's we know that the wheat seeds affects on the for example kernel's length, kernel length, or kernel width, or other type of the uh, physical characteristics of seeds. Yeah. So there is a single cause, but the main assumption is all of these effects, kernel length, for example, and kernel width, are conditionally independent given this cause. Yeah. So when we know the seeds, these features are not dependent of each other, which is a strong assumption. And in reality, this assumption easily violated. Yeah, even in this example. Yeah, most likely there is a dependency between kernel width and kernel length or other physical characteristics of seeds. So we should be very careful to use the naive Bayes classifiers. But even in the cases that this assumption is violated, still naive Bayes models perform well, similar to sometimes better than other models. And I will explain that um, what's the advantage, what's the disadvantage of using naive Bayes models in the last slide. So be patient with me. I will explain it how to use the naive Bayes models um, when we have the uh, real data. So as you can see, the total probability of the cause and effects, which is called the joint probability. This is called the joint probability. Equals to the probability of cause times this big pi is the symbol of the product of probabilities, which is the product of the effects, conditional probability of effects given cause. So The good thing about the naive Bayes is we can break it down, the joint probability, and we have the factorization. This is called the factorization, yeah? The right side of this equation is called the factorization. We can factorize the the joint probability distribution as a uh, product of the probability of the cause and probability of effects given the cause. Using this simple rule, which is called sometimes the chain rule, help us to compute the naive Bayes classifiers um, and the probability of each class. How can we do that? The way that we do it is, let's assume that we have a set of evidence. For example, assume that we know the kernel length and we know the kernel width, yeah, of the different seeds. And based on this evidence, we want to figure it out and compute or estimate the probability how likely this seed belongs to one of these three classes: Gamma, Rosa, and Canadian uh, classes. So the way that it works, we can if you just focus on one or two of these features, that means you technically ignored the other features, yeah. But this evidence can be a set of features that includes all features or just one of features. So it depends to you how many of the features you want to consider. In the seed example, I highly encourage you that use different set of features to see how that affects on your final results. And uh, is adding more features always improve the classification or not? Yeah, that's a very good example to practice. So assume in this example, only we have kernel length and we have kernel width. So that means technically we are gonna ignore the other features. So what does that mean in the language of the statistics? That means technically we marginalize out the uh, other observations, yeah, that technically we consider them as unobserved uh, variables. So how to do that? So I'm interested is, for example, I know the kernel width and kernel length. So I have evidence for kernel width and kernel length and width. L and W I'm using for kernel length and kernel width. And I want to see what's the probability that this seed belongs to one of these classes, yeah, Gamma, Rosa, or Canadian, yeah. So that's the main question. So based on the chain rule, this is equals to the right side of this equation that I'm showing with a star. And the thing is, since I have only evidence for length and kernel length and kernel width, I'm gonna marginalize out, which means summation over the other features and marginalize out those features that are not kernel length and kernel width. That's the technique. How it works is very simple. Let me show you in this slide how can we compute the probability of cause given a set of evidence. So the first equation is the chain rule. This one is the chain rule. And the second equation is the way that we are going to compute the probability of cause given that evidence. And as you can see, I'm going to write it down, this summation, using the chain rule, yeah, and expand it like this. So I use the first line, which is the chain rule, to expand the second line, the right hand of the second equation, to expand it as this big multiplication in the right side of the third line. So since I'm gonna marginalize out the y's, as you can see, some of these terms they do not have y, so they are not dependent to the y. For example, this one and this one, yeah. So I can write it down as a alpha p of cos sigma p of y given cos times p of evidence j given causes. And in the next line, you see that this part is gone. So that means technically this is equals to 1. And that's one of the well-known properties of the conditional probabilities, that in a conditional probability table, when you have the probability of EJ, different EJs, given a cause, yeah, given a cause, the summation of this column, if you sum them up, always equals to 1. That's one of the probability, conditional probability properties from the statistics course. So based on this rule, as you can see, the probability can be written very simple as P of cause times the P of evidence given that cause, yeah? And this evidence are those evidence that, or variables that are observed. So you see that all of them that are unobserved are gone. It's not part of this equation anymore. What is this alpha about? So when you multiply these probabilities, mainly this alpha is the normalization factor. Normalization factor. Which means it's very simple. For example, when you compute the probability of cause given evidence, in this example, for example, P of comma given kernel length, P of what's the probability that the seed belongs to the comma rosa, the second one is rosa, given kernel length, and the third one, P of Canadian seeds, given the kernel length. Yeah, you're gonna compute these three probability. And since this is a probability distribution, the sum should be 1. The sum of them should be 1. But when you compute this probabilities using this equation, I'm going to show it with a star, which is our main equation. So you may get different numbers. Yeah, for example, here you may get 0.02. For this one, you may get 0.05. 1, and for this one, you may get 0.03. Okay. And as you can see, the sum of them is not 1. How can we convert them to the probability distribution? You sum them up and you divide the probabilities that we obtain at the end by that summation. For example, the summation of them, if you sum them up, is 0.15. Yeah. So the normalized probability, in this case, this becomes 0.2, 0.02 divided by 0.15, which is 2 over 15. I multiply both numerator and denominator by 100. And in this case becomes 10 over 15, which is 1 over 15. 10 over 15, sorry. And for the last one, this becomes 3 over 15. So, and as you can see, the sum of these numbers, 2 over 15, 10 over 15, and 3 over 15, the sum of them becomes 1. So, and you can treat them as a probability distribution. And as you can see, for example, in this case, the second one has highest probability. So for that given kernel length, if you have a range of kernel length, that means that the seed belongs to the second class. Yeah, that's the way that naive-Bayes models work. Let me give you a concrete example based on the notebook that I shared with you on As You Learn. At least check it out. We have the variable, the feature that we are interested in is just kernel length, one feature between 5.5 and 5.7. At the top right, you see that the frequency of different uh, uh, type of seeds. The green one is the Canadian, the orange one is Rosa, and the blue one is Kama. And as you can see, they have more or less the normal distribution. And the way that this classification works is called Gaussian Naive-Bayes. So it's a Gaussian Naive-Bayes model. So what does that mean? That means you feed the data for each class as a Gaussian model. And as you can remember, a Gaussian model has a mean and variance. So when you fit it to the Gaussian model, the model learns the closest normal distribution that's a good fit for that type of data. For example, the Canadian, you can find what's the mean, yeah. And as you can see here for the green one, you can see the mean and the variance. And when you fitted the data to this Gaussian distribution, the model learns the mean and the variance. Okay, then you do what? Then you compute the probability distributions for each class. And as you can see, we have 70 elements in each class. So that means the probability of each class, comma, and the probability of Rosa, and the probability of Canadian seeds, probability of each class is 0.3, 33, or 1 over third, 1/3. Because each class has 70 elements, so 70 divided by 200 is 1 over 3. And so the probability of each class is 1 over 3. And then you need to compute the probability of um, kernel length given that class. For the first class, it's 30 over 70. And for the third one, the second one is 1 over 70. Only one of them, the kernel's length is between 5.5 and 5.75. And the third one also, there is only one seed that falls in this range. So as you can see, the probability of the class given this kernel length range, 5.5 to 5.75, you can compute the probability of each class given this kernel size. And as you can see, the highest probability belongs to the first class, which is common. So most likely, a seed with kernel length between 5.5 to 5.7 is a common seed. Yeah. And as you can see from the Gaussian distribution diagram, probability of each class, as you can see in the bottom right figure, you see you see that between 5.5 and 5.75, the highest probability belongs to the blue one, which is the common seed. So that's the way that the Gaussian naive-Bayes model works. So as a recap for this session, the naive-Bayes classification works in this way that, first of all, we normalize the data, then we fit the given data to a normal distribution based on the features that we are interested in. It could be just one feature or multiple features. And then in the given range, you look at the distribution that has the highest probability. That's most likely is your class. And the next session, we will discuss about different type of the classification models, and hopefully see you Monday in class. Stay warm and safe. Thank you.